So, in this course we will discuss about the electromagnetic waves. Okay. As the name suggests, the electromagnetic waves essentially consist two parts. One is the electric, another one is magnetic. Okay. And the rest part is the wave. Now we know that our of all universe we can say that our all universe can be divided in two parts. One is matter, another one is radiation or wave. Matter is characterized by its mass, but wave, in case of wave, there is no as such concept of mass. There is no mass in case of wave. So there are different type of waves. We are very much familiar with the sound waves and various mechanical waves, but also there is another kind of wave like light and other things. This light is an example of electromagnetic wave. I will come into that in details later, but now focus on these two parts, electric and magnetic. Okay. So in our universe there are basically four type of forces, as we know. First four forces are there. First one is our strong force, second one is weak force. The strong force and weak force are basically work in very in the micro level, like inside the atoms or the electrons, proton. In that case, the strong force and weak force are basically works. Another force is the gravitational force. Okay, we know that due to the gravitation, every body, everything actually attracts each other. And another one is our electromagnetic force. So basically this electromagnetic force, this force is essentially related with our electromagnetic waves. Both things actually consist that electric and magnetic field. So before entering in details in about the electromagnetic waves, we should understand first what is the electric and the magnetic field. Okay, let's start with the electric field. Let us say there is a point charge q. Then around this point charge q there should be a field which is called electric field. Now what is the definition of this electric field? Let us say if we consider another charge that can be plus or positive or negative, if that positive charge here resides here, then there will be no attraction or repulsion. But if we take this positive charge into this field, then there will be attraction or repulsion. So by this way we can define the area under which the power attraction or repulsion due to that point charge works. That is called the field around that charge. So this electric field essentially denoted by the E, and F is Q times E, where Q is the charge of that particle charge, and this is the electric field and this is electric force. Okay. And similarly there is also magnetic field. Let us say if we consider one magnet, there is north pole and south pole. So around this magnet there is also one field works like same like the electric field. So and its works in a same fashion. So B is denoted, B is the magnetic field. The equation the force acting due to this magnetic field is not straightforward like this electric field. So for that we use Lorentz force, we will come to that, but this is the magnetic field. So one thing we should notice, in case of electric field I draw up electric charge, but in case of magnetic field we need to consider two poles, at least two poles, because there is as such no concept of monopole, okay, in case of magnetic field. So there is no concept, but in case of electric field there is monopole is there. So, but in magnetic field there is no concept of monopole exist. So, now okay, so first electric field and magnetic field we understand. Now, let us say consider a particle, let us say this is the axis, one particle is there, any particle, a charged particle obviously, and it is moved in v velocity in, let us say it is x direction, it is x, it is y, z. Then if we apply a electric field through x axis in this way, electric field, and through this magnetic field, then there will be a force acting on due to the electric and magnetic field on this particle, charged particle, which is called Lorentz force. These things are important to understand electromagnetic waves. So, that is why I discuss. This is the Lorentz force, which is Q times E plus Q V cross B. So, this is the formula of our Lorentz force. This is due to the electric field and this is due to the magnetic field. Two forces are there. Actually, what happens? This we discuss, we studied electric field and magnetic field separately, but actually what happens that electric field and magnetic fields both are equivalent to each other. If electric field and magnetic field are actually related, why? Because if there is oscillating electric field or accelerating electric field that produce magnetic field, and the vice versa, if there is a accelerated changing the magnetic field which is changing with the times, that can also create a magnetic field. Just like if a current flows through this wire, then around the wire, because the current is flowing, that is why the electric field is also changing with time. So, that is why around this wire there will be a magnetic field as well. And similarly, if we change the magnetic field with time, then also the electric field will produce. So, essentially the electric field and magnetic field are related very much, and electric field can produce magnetic field can also produce the electric field. So, this is the key element for the electromagnetic waves. To understand the electromagnetic waves, we understand that electric field and magnetic field are associated each other. Okay. So, let me start with the Maxwell's equation. There are several forms of Maxwell equation. I will discuss first the differential forms. 4 Maxwell equations are there. Okay. So, first equation is this is the divergence. This is in general equation. This is the general differential form. Second one is 0. Third equation is these are the 4 Maxwell's equation. So, this is general because and it is in differential form. We can see this is these two are divergence and these are the curls. Okay. So, first we understand this equation, then we will discuss. Okay. Okay, here what are the things like D. D is okay, first row. This row, this is electric charge density. J is electric current, which is defined as sigma times E. Next is our E is the electric field, B is the magnetic field, and D okay, first B is mu r H, and I think D, yes, D is mu epsilon. Okay, so this is our equation, but now in vacuum we will study the Maxwell equation in vacuum. In vacuum our rho is 0, sigma is 0, that we can write the mu r equals to mu naught, and this is actually relative permeability, this is relative permittivity, I am not writing, and this is in vacuum mu 0 and epsilon 0. So, in vacuum our Maxwell equation will be much more simpler. So, what will be the 4 equations now? Let us H, because okay. So, these are the 4 equations. So, it can also be written as, instead of B we can write H, because B equals to mu 0 H. So, these are 4 equation. This equation, first equation is called our Gauss law for electricity. The second one is Gauss law for magnetism. This fourth one is Faraday's law. And this is our Ampere Maxwell. So, essentially there are 4 laws. So, now these are the 4 Maxwell's equation are there. So, these Maxwell equations are valid for only vacuum. Now, we can see there are 2 fields, right, electric field which is denoted by E, and another one is the magnetic field which is denoted by H. Okay, so, we can see from the third and the first and the second equation are the divergence of the electric field and magnetic field in vacuum is 0. That means that in vacuum electric field and magnetic field can't be produced automatically. If the divergence is 0, that means automatically there is no source essentially. If there is any source in vacuum, then only the electric field and magnetic field will be produced if the divergence is non-zero. But here we can see that from the first and second equation the divergence is 0, which means that there is no as a source in vacuum which produce the electric field and magnetic field. But we can see from third and the fourth equation the curl of the magnetic field and the electric field, that the curl of the magnetic field is related with the this one, the curl of the magnetic field, this is the curl of the magnetic field is related with the change of the electric field with time. That means if del E del T is 0, that there will be no curl of the magnetic field, which means if the electric field changes with time, then only the magnetic field will be produced. And from the fourth equation we can see the reverse one, if the magnetic field, okay, there is a minus sign, yes, okay, if the magnetic field is changing with the time, then that creates the electric field. So, it is clear that if there is oscillating electric field or magnetic field, because oscillating field means that is the accelerating field. So, in case of oscillating electric field, that will produce the magnetic field, and that magnetic field will also be oscillating, which again produce the electric field, and this simultaneous reproduction will essentially create the electromagnetic waves. So, okay, I will come into that, the direction and the orientation of the waves. So, first let we study these 4 equations, the outcome of the 4 equations. So, first now let take the curl of our equation 3. Okay. So, it will be, we can write in this way. Okay. So, this is our first equations, just we put, instead of using the third equation we can easily write this. Okay, this is also epsilon 0, this epsilon is Okay. So, here we can write this is the del h minus del square h plus an operator equals to epsilon 0 del del t del e. Okay. So, this is okay. We using the equation 4 we can write this is minus sign, no, it's okay. So, it is minus mu 0 epsilon 0 del h del t square. Okay. So, this is also 0. So, del square h equals to mu 0 epsilon 0 del 2h del t square. So, this is a wave equation. We know in case of our mechanical wave, in case of sound wave also, this is a general form of wave equation. General form is del square psi is equal some velocity, actually it is 1 by v square to, this is our general equation for any propagating waves. We can write this equation where psi is the wave function. So, then we can relate two equation and we can see that v should be 1 over mu naught epsilon naught in vacuum. So, this is we are considering as electromagnetic radiation, and light is also electromagnetic radiation. So, in generally it is written as c instead of v. So, this is the speed of the light. So, again we can derive the same equation using the electric field as well. So, that will be del square E equals to mu naught epsilon naught this. So, from this equation we can estimate theoretically the speed of the light, which is in vacuum, which is this one. Okay. Yes, correct. So, this is our speed of the light, and in general if we do not consider the vacuum, in general it will be mu epsilon. So, now we can replace mu is equal to mu r mu naught, what is happening, and epsilon is equal to epsilon r epsilon. So, this is our general formula, mu naught mu r epsilon naught epsilon. Okay. So, these two has the standard value. If we put these values in here, then we can evaluate the value of c, which is around 3 into 10 to the power 8 meter per second theoretically, and experimentally also we can confirm that our speed of the light is also matches with this theoretical result, which essentially supports that light is a electromagnetic radiation. Okay. So, but now we have to characterize our electromagnetic waves from these 4 Maxwell's equation. Let me start. So, this equation or the previous one as we written, this one, these two equations are basically the differential equation. We can solve this equation. So, what will be the solution of this equation? E is equal to E naught. E naught is the amplitude of the electric field equals to e to the power n. Okay, vector sign will be there obviously, kr. Okay, this del operator consists r basically. So, in one the form of this del operator is d2 dx2 plus d2 dy2 d2 dz2 in Cartesian coordinate. In polar coordinate there will be r. So, it will be minus. Okay. So, the same form. What is k here? K is the wave vector. We know that for any wave, any mechanical wave, the wave vector is very crucial thing, very characteristic thing of that wave. So, here we can write k equals to kappa. Kappa is the magnitude of that wave vector and times n. This n, this is the unit vector along the direction of wave propagation. Okay, and this is the magnitude. Oh. Okay, so this is our k wave vector. So now using these two equations, these two are very important. So here we can see that this E electric field is also oscillating with the time, because time is there, and similarly the magnetic field H, both fields are oscillating with time. So we can individually we can draw this like this way, oscillating electric fields or magnetic fields, but here we can see that both electric and magnetic field present simultaneously. So then in that case, what will be the pattern of our electromagnetic waves? Okay, one thing, as when we draw for any waves like this, here y, x, so this is actually snapshot of the wave. That means this is for a particular time. After some time, what happens, these particles oscillates. If we consider our sound wave or mechanical wave, in that case what happens, the particle oscillates. So after next time the wave will be like this, and also in between all points are also considered. So when we draw waves like this, we should keep in mind that this is actually the snapshot of a particular time. Okay, thank you.